So just our introduction on section 4.1, we are going to talk about increasing functions, decreasing, and concavity. So let's talk about what it means to be increasing. So we can say a function is increasing if f of x sub 1 is less than f of x sub 2. So for example, when you take a look at this first graph, the y value at x sub 1 is less than the y value for x value of x sub 2. So that's what it means that f of x sub 1 is less than f of x sub 2. And if that happens, we can say it's increasing on a particular interval. We say that f is decreasing on the interval if f of x sub 1 is greater than f of x sub 2. So if you take a look at the second diagram, notice the y value at x sub 1 is greater than the y value at x sub 2. So we can say that this function is decreasing in this particular interval. We can also say that an interval is constant if the two y values are the same between an interval. So this leads us to a theorem that f has to be a function that is continuous on a closed interval a to b and differentiable on an open interval a to b. So this is going to talk about increasing and decreasing in the first derivative. If f prime of x is greater than 0 for every value of x in the interval, then we can say it is increasing on the closed interval. If f prime of x is less than 0 for every value of x in the open interval, then we can say that f is decreasing on that particular interval. If f prime of x is equal to 0 for every value of x, then we can say it is constant in that particular interval. Now when we're doing justifications, there are some ambiguous words that we're going to need to avoid this year. So one word that we're going to need to avoid is referring to it. We always want to refer to a function as its name, f of x, g of x, etc., not it. Graph, the graph. Again, the graph has a name. Is it f of x? Is it g of x? Is it h of x? Slope. We will use increasing, we will use the words decreasing, or derivative. We talk about up or down. So those are some words that we're going to need to clarify or not use in our justifications. So for example, example 1, find the intervals where f of x is increasing or decreasing. So what we first want to do is we want to find our first derivative. So using the power rule, this is going to give me 3x squared minus 6x. So what we want to do is we're then going to take the first derivative and set it equal to 0. So 0 is equal to 3x squared minus 6x. So I can factor out a 3x, and that's going to give me an x minus 2. So when I set these equal to 0, these are going to become what we call my critical numbers. So the x equals 0 and 2. So what we want to do, this is where the first derivative is equal to 0. So what I want to do is I'm going to plot these on the number line. And I'm going to do my number line test. Remember, if my first derivative is greater than 0, I know I'm increasing in an interval. So if I pick a number less than 0 and I plug it into this particular function and it's positive, every number less than 0 will also be positive. So if I plug in -1, you don't have to find the actual number, just find whether it's going to be positive or negative. 3 times -1 I know is a -3, so that's a negative number. -1 minus 2 I know is a negative number, and a negative times a negative is a positive. So since -1 gives me a positive output, every number less than 0 would also be positive. I want to pick a number between 0 and 2, so let me pick 1. 3 times 1 is positive. 1 minus 2 is negative. And I know a positive number times a negative number is negative. So that tells me that this would be decreasing from 0 to 2. And then finally, I plug in a number greater than 3. 3 times 3 I know is positive. 3 minus 2 is positive. So this is going to give me positive. So I know that every number greater than 2 is a positive number. So I know since f prime of x is greater than 0 on the intervals negative infinity to 0, and 2 to infinity. Therefore, f of x is increasing. So f prime of x is less than 0 from 0 to 2. Therefore, your f of x is decreasing. So that's how you can talk about whether a function is increasing or decreasing by looking at the first derivative. So not only can we talk about finding whether or not a function is increasing or decreasing, we can also look at concavity and derivatives. So we can say that f is going to be concave up on the open interval if f prime is increasing on that interval. F is going to be decreasing if f prime is decreasing. So to be concave up, notice what's happening. F prime is my slope. Notice the slope of all these tangent lines are increasing. They're getting larger and larger. So I know it's going to be concave up. When they say that f prime is decreasing, notice the slope of my tangent lines. They are getting smaller. They're going from positive to 0 to negative. So that's how I know I'm going to be concave down. So that's what we mean by increasing slopes and decreasing slopes. So now we're going to look at the second derivative. So f, first of all, has to be twice differentiable. If f double prime of x is greater than 0, then f is concave up on that interval. So remember, concave up is up like a cup. So if the second derivative is greater than 0, then we know it's concave up. If we're less than 0, then it's going to be concave down. And remember, concave down is the upside down u. Find the interval where f of x is concave up and concave down. So you have to find the second derivative. You can't find the second derivative without first finding the first derivative. So f prime of x is going to be equal to 3x squared minus 6x by your power rule. The second derivative is going to be 6x minus 6. So just like we did to test for increasing and decreasing, we're going to take the second derivative and set it equal to 0. So x is equal to 1. So we still have to do the number line test. And again, this is for my second derivative, so I always like to label my number line. Again, so if I plug in 0, a number less than 1 is 0. 6 times 0 is 0. 0 minus 6 is negative. So I know numbers less than 1. I know I'm going to be concave down. If I plug in 2, 12 minus 6 is positive. So that tells me I'm concave up. So since your second derivative is greater than 0 in your interval 1 to 2, I know that f of x is concave up. Since my second derivative is less than 0 from negative infinity to 1, f of x is concave down. So this leads us to our second, another theorem. If your function is continuous on an open interval containing an x value, and if f changes the direction of its concavity at a particular point, then we say f has an inflection point at x sub 0. So again, this point right here, that x sub 0, this is our inflection point. Again, it changes concavity at that particular point. So it changes from a concave up to a concave down, or it can change from a concave down to a concave up.